Welcome back to the video lecture series for Introduction to Periodic Programming using Scala. In this video, we're going to continue looking at our work and working on our implementation of quadtrees. We're doing a region-based quad tree here. And in the last video, we got through the code to actually make the tree. Our base case, if the number of points is small enough, is we simply set those points into the node, and if it's larger than that, then we set the children to be an array with 4 nodes in it. Note, we have not actually tested this code, but that will come in just a bit. Before we can test it, we have to be able to call, we have to write code for the visitation. So how do we do visitation on a region-based quad tree? The idea is if I want to find the neighbors of some point right here, I start at the root. And the root obviously encompasses everything. And then I have to make the decision, do I have to recurse into each of these 4 subregions, and then recurse into those, and recurse into those. Obviously, if I get to a leaf, then I'm not going to recurse any further. I just compare against the points that are in that leaf. We know that we have a leaf if the number of children is equal to 0, and that if the number of children is greater than 0, we have to check for recursion. So let's go ahead and we'll start with that base case. We'll go ahead. This should be, this needs to be done recursively, so I'm going to write a little function that just does a recur. We'll pass in the node here, and it should be able to get most of the other information from what was passed into the top level function. We'll play with that. How about if children is empty? Yeah, that'll work. Well, then what we want to do is we want to call visit on all of the points that are in this node that are close enough. You know, that looks a whole lot like the brute force algorithm. So, except this is p in dot points, and if the distance from P to point is less than whatever, then we do a visit. And I'm just going to compact this code a little bit. Okay, so if we're in a leaf, we run through. Else, what do we need to do? So that we don't forget it, let's go ahead and let's call recur on the root down there. Well, in this case, we have children, and we need to check if if the area that we're searching overlaps with the children, and then recurse into them if that's the case. So, how do we do this? Tempted just to keep this quick, instead of actually intersecting with a circle, I'm going to intersect with the with a rectangle that is centered at this point and has an edge length that is 2 times the search distance. So if P and T sub 0, the x coordinate, plus, let's see, actually our children here, the sub 0 is plus plus, the sub 1 is plus and minus, the sub 2 is minus and plus, and the sub 3 is minus and minus. So for sub 0, whether or not we go into there, I would have to have the point sub 0 has to, that plus search dist needs to be greater than, technically, or equal to the CX value. So what does that mean? If we are greater than, and this should be n dot CX value. If that's the case, when we go and we look at our image here, so if I have, consider these four regions here, I have a circle that goes around a certain point, or basically you can think of it as a square. If the search distance added to the x is large enough that some of it can cross this line, well, that's what this is saying. I will go into the first area, which is x plus 1 and y plus 1, if I have both the x satisfies this and pnt sub 1 plus search dist is greater than or equal to n dot cy. In that situation, I have to do a visit neighbors on the same point, the same search distance, and the same, whoops, I'm not calling visit neighbors, sorry, I'm calling recur, because all those things are the same. Recur on n dot children sub 0. Okay, so what about the others? Our next case is x is still positive, but now the y was minus, and so we want to check to see if the y value minus the search distance is less than this. For the other two, both of the x's were negative. I still have something I need to change. And then here, we're also negative. So greater than, less than, plus minus, plus minus, plus plus, minus minus, greater than, less than. And when we recurse, this should go to sub 1, this should go to sub 2, and this should go to sub 3. Okay, so note that if the region doesn't touch a square, we don't recurse there. So what order is this going to be? Turns out for a region-based quad tree, the answer to that question is a little bit tough. This is going to go as long as the search radius is fairly small, we don't expect this to branch too much. Down at the bottom, okay, it might branch a little bit, but most of the way down the tree, it's going to go to, for example, one child. And so if you only go to one child, if you're not doing a lot of branching because your search radius is small, then you wind up basically going and doing one recursive call per level of the tree, down until you're close to the bottom. So the work there goes as the number of levels. The question is, and for most trees we'd say the number of levels is order log n. For the region-based quad tree, because of the way this splits up with regions, that isn't always going to be true. You can see just looking at this tree isn't well balanced. Okay, so these areas in here go much deeper than this, and that is one of the reasons why you might choose to not use a region-based tree. For most distributions, this will probably still come out fairly close to log n, but you actually can come up with some horrible situations where you have one point way over here, another point way over here, another one here, another one here, and then all the rest of your points are lumped down right by the middle. That would be a very bad situation for the region-based quad tree, and it would do a lot of additional work. But that type of case is unusual. I will say that when I've used region-based quad trees in the past, it has often been because I had data associated with the tree that I put at intermediate nodes. So my internal nodes had additional data that was associated with them. Not always the points. Sometimes they are the equivalent of the points, but other times they're other things. So we'll come back in the next video and we'll look at the last type of spatial tree that we're going to talk about, the KD tree, and it actually will be perfectly balanced because of the way that we're going to construct it.